Hello, good morning from Waterloo. Just checking if everyone can hear us and see our screen as well.
Yeah, we can hear you from it, yes.
Okay, all right, great. And you can see the screen?
Yes, we are.
Okay, all right, great.
Hello, here is Yafti. We are okay.
Okay, great.
Why do you know what you want to change? No, I don't want to change.
Can you get somebody? Yeah.
Good morning, everyone. Hello, do we have everyone?
Good morning, Professor.
Good morning. So was that ETS?
Yes.
Good morning.
Hello, is that Toronto? Or is that Laval?
No, it's Toronto.
Toronto, okay. How about Laval? Do we have Laval here? Laval, are you there? Okay. I think you are muted, Laval, right? But you're there. You can wave. Anyway, it is 9:30. I think we can start our lecture. So today is the interactive session corresponding to the video recording and the slides that you received earlier in the week, and they are dedicated to network virtualization. So network virtualization is slightly orthogonal concept to softwarization, but very much related. As a matter of fact, it predates the movement of softwarization, but there are a lot of commonalities, and they work together nicely, and that's why I think we're covering network virtualization here, as it can work very well with software-defined networks, for instance, and that's basically what we covered in this particular class is the main benefits. Let me maybe go through the slides here. Right here, yeah. So obviously, like the other lectures, the objective here in this case is mostly to learn about network virtualization and the key mechanisms underlying network virtualization, as well as finish with providing you with what's basically happening in the area of network virtualization research and the lecture materials. Can I ask you to please mute your can you mute? Yeah, I see someone in some transportation here in a train or a bus somewhere. Okay, thank you. All right, so the material started with basics, definition, what is network virtualization, the business model, because this is obviously a transformation on how networks are designed and operated and managed, and what is the underlying business model, and provided examples also of what's happening in the mobile networking world, and discussed the benefits and some more recent use cases, notably the concept of 5G slicing, if I recall correctly. And 5G slicing, these are the next generation or fifth generation of mobile networks, and slicing is, you can think of it as synonymous to network virtualization, except that maybe in addition to partitioning and allocating bandwidth and processing capability or resources, in addition to that, 5G network slicing involves also the instantiation of virtualized network functions along the path, in addition to storage and processing resources in edge and core clouds, and bandwidth resources in the wireless access, as well as the front haul, back haul, and optical transport core networks. We also covered the lecture materials covered the mechanisms that are part of network virtualization, and these are typically the abstraction of physical resources, abstracting their physical characteristics, the partitioning of the resources, and the resources can be partitioned in many different ways. There is the so-called hard partitioning and soft partitioning, and very important concept also in network virtualization is the concept of isolation. You would like that coexisting virtual networks on the same physical network are provided in a way that they are isolated from each other, which means they do not interfere with each other. Interfering in terms of performance, they don't affect the performance of each other, or for example, they are somehow secure. They can basically, there are no security, basically there are no leakages that lead to security vulnerabilities, since you will have multiple tenants on the same infrastructure. Then obviously virtualization can take place at many levels. At the node level, right? So remember, a network can be abstracted as a collection of nodes, and a collection of links are interconnected by links. And so basically there is virtualization of single nodes, and here the node can be a switch, can be a router, can be a network interface card, or any combination thereof, and there are links, and the links can be implemented using different media. They could be wireless links, they could be optical links, it could be something else, and obviously the virtualization of these different nodes and these different links is different, right? We don't virtualize links of different medium the same way, and we can implement link virtualization also at different levels of the protocol stack, right? We can do partitioning at the physical layer. That's mostly hard partitioning, but we can do it also at the upper layer, up to the application layer. And then the more we go up the protocol stack, the more the partitioning is soft, I would say. And because it is soft, the isolation is less significant, right? Obviously, if you do a hard partitioning and you allocate different physical links, then the isolation is really good, right? Because there is no interference. If you do soft partitioning, then there is less isolation. Eventually, more potential for interference. So there are pros and cons. There are trade-offs, obviously, and virtualization actually exists and has been implemented at all these different levels, and the lecture material is covered all of that, right? Then you can virtualize the network as a whole, right? So basically virtualizing the nodes and virtualizing the links and then virtualizing the network as a whole consists in this idea of creating a logical topology consisting of virtual nodes and virtual links that are mapped onto physical nodes and physical paths respectively, right? And then you want to do that in a way that optimizes resource utilization and so on and so forth. There are many, many different optimization objectives that you want to achieve, you try to achieve while doing this network-wide virtualization, okay? And then the class also material covered SDN virtualization, since we are obviously here interested in softwarization and see how these two work together. SDN virtual software-defined networks and network virtualization, and how this work together. For example, how can we create multiple virtual networks that can be all softwareized, basically controlled independently of each other, and so on and so forth. And how, for example, we can leverage network softwarization or SDN, for example, to perform or implement or realize virtualization. For example, by for example, Flowvisor that partition the resources logically by partitioning the flow space as opposed to partitioning the hardware resources, just partitioning the flow space and allowing the creation of multiple software-defined networks that can be controlled separately. And then the lecture materials, I think, at the end covered some of the research challenges and research directions in network virtualization. So that's basically an overview of what the material for this particular class covered. So with that, I'm going to open the floor for questions and whatever these questions are throughout the course material. So please do not hesitate whenever you have one.
Hello. I have a question.
Go ahead.
What is the difference between the network business model and the mobile network model? Are they both the same thing? Just the different representations?
When you say the network business model, you are referring to slide number 9?
Yeah.
Yeah. There is no difference, really. I think the slide 9 describes a general business model, right? It represents the main idea of decoupling what used to be one single role in traditional networks. So in traditional networks, you have a network provider or a network operator, called a different name for the same thing. And that network provider basically owns the infrastructure, basically buys switches and links, deploy these, then deploy services on top of these physical infrastructure that he owns and manages, and then provide services to end users, subscribers. That's how traditional networks work, right? So in the network virtualization business model, the idea is to basically decouple this traditional network provider role into two main roles: the infrastructure provider role and the service provider role, right? And so the infrastructure provider owns and manages the infrastructure and leases resources to different service providers that deploy services and make them available to end users or subscribers, right? So that's the general concept of decoupling the role of traditional network provider into service providers and infrastructure provider that can be completely different entities, okay, different business entities. Sometimes the infrastructure provider can also provide services. So there is of course can be any combination of that. But mainly the idea is to have these two separate roles. Now that's the general or generic business model. Now what you have seen, and I think that relates to your question as to what is the difference with the network virtualization in mobile networks. There is no difference. This is just an example, a real world example where network virtualization has been basically used to segment the networking market into multiple such roles, okay? And in this example, you see that we have more than just two, right? You have more than just two. You can, and again, you can have more than that, right? But this is an example of what's happening in mobile networking world. So it is one example of a virtualized environment or a business environment for involving network virtualization that implements the previous general model that I described in the previous slide.
Here, what do you call the hypervisor, which partitions the resources, is done by the virtual network operator, right?
Say again?
In the later slides, you said something about the hypervisor, which partitions the resources and provides it to the services and all. So that is done by MVNO, right?
This is basically, in this example, if you're looking at this example, it will be the MVNP. In this particular example scenario, it is the MVNP that will partition the resources and allocate that to MVNOs that will operate these resources. But they can be the same thing, right? So you see, that can be a mobile network operator that acts as both INP and MVNP, in which case the MNO will provide this resource partitioning. Not necessarily using hypervisors, right? Because hypervisors are typically used for, for virtualizing server resources, computing resources, right? So there are different technologies that are used here in networking, and these are covered, and these different technologies are covered in the material. Okay.
So in mobile networks, the resources means the antennas and like all those things, right? The bandwidth. In the mobile networks, the resources maintained by the infrastructure provider means the bandwidth, the antennas, and all of those stuff.
There are many different things. Of course, there are so in this case, the virtualization can go all the way from, say, for example, assuming you have. This is happening, for example, in the area of the mobile networks. So you have, for example, companies that own the antennas, basically the towers, not really the antennas, the towers on which the antennas are deployed, right? And so instead of having like the network operator that deploys towers and then put antennas, and each network operator have its own towers and its own antennas, instead of that, you have companies that only owns the towers. Basically buy the land, deploy the towers, okay? And then lease space on these towers for network operators to deploy antennas, right? Then the antennas, basically, process the radio signals and whatnot. So basically here there is a spectrum, and spectrum is the bandwidth you mentioned, and this is one of the resources that can be partitioned and allocated to different network operators, okay? So you can allocate resources. Here are obviously the spectrum, the wireless spectrum, that is partitioned and allocated to different virtual networks. But there are also other resources, okay? There are other resources in the core of the network, in the access of the network, eventually at the edge of the network, such as, the base station controllers, or if you're talking about, for example, 4G and 5G networks, that will be all the different functions involved in the included that are part of the evolved packet core. So resources can be nodes, but can be also link bandwidth, et cetera, similar to other network environments.
So these are everything managed by the softwares in the different stages, like the partitioning and all, or is it a hard partitioning?
Can you speak in the mic here, because I'm not hearing you?
So this partitioning, which is done in the allocation, is it done in the software part, or is it like a hard partitioning?
That depends on what technique that you are using. It can be done in the. It can be done. It could be hard partitioning. It could be soft partitioning. There are different techniques that are used. So obviously, if we're talking, so or a combination thereof, right?
And the slide number 13.
Okay. Go ahead. Slide number 20. But after that, we're going to pass the
13.
The mic to somebody else. 20.
13.
Yes.
So is this the logical connection which you are mentioning in the virtual data centers?
Okay, so these are examples of topologies. Okay, so remember here, the idea is to virtualize data centers, right? So here, what you see in the previous slide 12, you see we have a physical data center. That's the bottom of the figure here. So this is the architecture, or a typical architecture of a data center. So we have racks of servers. That's the black boxes here. So basically a rack on which there are many servers, and there is a top of a rack switch that interconnects these servers together in the rack, but also connects the rack to other racks in the data center. And this interconnection is done through layers of switches, typically a tree structure of switches and links that allows any server or any virtual machine deployed in a server to communicate with another virtual machine in another server. And these layers of switches are then connected to a layer of routing that interconnects the data center to the rest of the world, to the internet. Okay, that's a physical data center. And the way it works traditionally in data centers is that mostly virtualization involves compute and storage resources. For example, if you go to Amazon EC2, you say, I want a virtual machine instance with so many CPU cores and so much memory and so much storage, right? And you are allocated that, right? But very often, you deploy applications in data centers that consists of more than one single virtual machine, right? And this virtual machine may communicate together, right? And so you can have multiple applications that share the same data center. So there are multiple tenants or multiple tenant applications that coexist in the same data center. These applications receive virtual machines with guaranteed CPU, memory, and storage, as I mentioned. However, they do not receive guaranteed bandwidth that allows to isolate the communication between the virtual machines in one application from the communication that take place in other applications, all right? So say, for example, if you have one application that uses a lot of bandwidth, okay, or exhausts all the bandwidth resources in the data center network, this will affect negatively all the other tenant applications in the data center. So far, so good?
Yeah.
So the idea of virtual data centers or data center virtualization is to offer bandwidth guarantees in addition to CPU, memory, and storage guarantees. So not only we allocate to applications virtual machines with guaranteed CPU, memory, and storage, but also a guarantee in terms of link bandwidth between the different virtual machines that are part of an application. And that is called a data center, a virtual data center. And if you look at the picture here, it is illustrated by the two examples, the green and the blue virtual data centers. So a virtual data center is composed of virtual machines, okay, as well as virtual switches and virtual links that interconnect these virtual machines. And this is how you guarantee bandwidth in addition to CPU and compute and storage resources, okay? And you can see here that these different virtual data centers will coexist on the same substrate data center, physical data center, in isolation without interfering with each other. Now the question is, I think the next slide, and that's your question, is to what this correspond, this whatever topologies or these logical interconnections between in these example applications. Yeah. So the purpose of this slide is to illustrate, to give you examples of application that need these virtual data centers, okay? To motivate why do we need virtual data centers, and give you some examples where we not only need virtual machines with guaranteed computing and storage resources, but also bandwidth resources between the different virtual machines. And these are three popular topologies of such virtual data centers or applications that are deployed in data centers, in cloud data centers. The first one is a multi-tiered. And this is typical for when you deploy a web service application. A web service application, typically you have a web dispatcher, okay? And here we have two instances of a web dispatcher. At the beginning, then you have application servers, okay? And this is the middle tier here, right? And you have two instances of the application server, a front and up. And then we have a back-end database management servers, okay? And here we have also two instances of these database management servers. So you deploy in this your application two virtual machines as a front end, basically to load, balance, and dispatch web requests. You deploy two application servers, basically to handle the load, and two database management servers, basically to respond to the actual web request, to fetch the web objects and deliver them to back in response to requests. Now, this is the way it works is that they are interconnected with each other. So basically, the web dispatcher receives the requests, passes the request to the application server, one of them, which process it and then send it to one of the database management server to obtain the web object. So they are interconnected in this way, okay? So here, in this case, if you want your application to achieve the expected performance, you have to allow basically to deploy virtual machines for the different servers, but also virtual links and eventually virtual switches that interconnect these different components of this three-tier web service application, okay? So that's a multi-tier interconnection. The second example is a partition aggregate graph. And a partition aggregate graph is useful for query processing type of applications, okay? And then the third example is a bipartite graph. And a bipartite graph is typical for those applications, typical cloud application that do parallel processing of big data, for example. These are, for example, MapReduce applications or Spark applications, okay? Where you basically partition the data and allocate the data to multiple different virtual machines so they can process the data in parallel and you are able to achieve good performance this way. So these are commonly deployed application in the cloud that can benefit from the concept of virtual data centers, because not only they are guaranteed the compute and storage resources, but they're also guaranteed the bandwidth resources that interconnect the different virtual machines. Is that clear?
If I get it right, this is
okay. Can you hold on for a second? Maybe see if someone else has questions somewhere else.
Yes, there's a question from. What's the difference between the VLAN and virtual LAN and LAN virtualization?
What is the difference between VLAN?
Virtual LAN and LAN virtualization.
There is no difference necessarily. VLAN is technology. LAN or local area network virtualization is a concept. You basically take a local area network and you virtualize that. Now you can virtualize that in many different ways, okay? And you can do it at different layers of the protocol stack. So VLAN is one specific technology that achieves LAN virtualization, okay? At layer 2, there is also VXLAN. There are other MPLS to some extent can be also layer 2 virtualization. So that in general, it's not really deployed in a local area environment, but anyway. So there are many different technologies that implement LAN virtualization. Okay.
One question in the page 30.
Go ahead.
Since the VNIC and the V switch are connected to each other, then why you said
which slide? Sorry.
Slide 30.
30.
Why you said here do not support guaranteed bandwidth? Because here is not use some virtual link.
So how do we get guaranteed bandwidth here?
Yes.
Oh, it's not strict guarantee in this case. You know, this is more a soft partitioning of resources. Basically, you rate limit. Say, for example, you say, okay, I have, say, for example, whatever, 100 megabit per 100 megabit capacity, and I'm gonna deploy, say, 10 applications. Each of them is gonna get approximately 10 megabit per second, for example, capacity. So basically, you deploy these applications, and then you rate limit. Any application that exceeds 10 megabit per second, then you basically throttle the application, or basically you drop the excess of traffic. So this is one approach of implementing soft partitioning and indirectly providing some level of guarantee, right? If you allow no application to exceed the 10 megabit per second, say, then all the application will get more or less the 10 megabit per second if they have traffic to transmit at 10 megabit per second. This is not hard partitioning. We are not really dividing physically the bandwidth here, okay?
Okay, so it's SDN to solve the problem to support the guaranteed bandwidth?
I'm sorry, I could not hear you.
Is SDN as a solution to solve here as a guaranteed bandwidth?
Not really. No, SDN Well, you can use SDN, of course, for some flow scheduling and things like rate limiting and things like that, but it doesn't really solve it. You can use SDN to implement these mechanisms as well.
So the guarantee bandwidth can only be implemented as a physical multiplexing, for instance.
Hard guarantees. Again.
Hardware guarantee.
Yeah, hard guarantees. Hard guarantees means 100% sure, right? The resource is dedicated. So the advantage of hard partitioning is that when you do partitioning at the physical layer is that you are guaranteed these resources. But there is one problem with that. You have very little room for optimization. For example, if you allocate in a dedicated manner a subset of the resource to a particular application or a virtual network, then no one else can use it. So that's why it's hard guarantee. The disadvantage is that if that virtual network doesn't use it, then it is wasted. Okay, nobody else can use it, right? So with soft partitioning, you have room for optimization, right? For example, if you say, again, take the example of I have 100 megabits per second capacity link, and I'm supporting, normally each application is supposed, or each virtual network is supposed to get 10 megabits per second, then I can support at most 10 applications or 10 virtual networks at the same time. But since I know that not all the virtual network will be using their resources at the same time, instead of allocating it to 10 virtual networks, I'm going to allocate it to, say, 12 virtual networks, with the assumption that not all of them will be using the resources at the same time. And this way, leveraging so-called statistical multiplexing and improving resource utilization and thereby revenue of the infrastructure provider. So there are actually advantages and disadvantages. There are pros and cons to hard versus soft guarantees of network resources as part of virtualization.
So do you mean that the soft guarantee bandwidths are optimized by the algorithm between the VNIC and the VSTREAM?
Yeah.
Okay.
Well, it can be in the controller if it is SDN. It can be implemented in many different places, right? It's not really necessarily in the VNIC. Okay. It should be at the virtual switch level, basically at it's in software, obviously, but it is in the whatever the virtualization platform in this case, the hypervisor in a compute environment, or the virtualization platform in the case of switching equipment.
So how can we quickly deploy the services for instance, for some cloud for a guaranteed bandwidth?
What do you mean by quickly deploy the services?
For instance, a cloud requires suddenly a very huge bandwidth, guaranteed bandwidth to support some instant services.
Okay.
But the physical switch, physical bandwidths are limited by the telecommunication providers. And since you ask for increased bandwidth from the CPs, it needs quite a long time to implement a ticket.
No, you cannot. You cannot give more bandwidth that you don't have. If you reach the full capacity and you have whatever request that needs more bandwidth than you have, then you cannot support it. Then the request is rejected.
So there is always a conflict between the data center and the network operators.
No. The data center provider is the network operator here. It's not two different entities. Here, the data center, if we're talking about
communication provider like routers or the FIDO, which provides some physical bandwidth.
Are they inside? Are these switches or routers inside the data center or outside?
Outside. Some extra companies for only the data center.
Yeah, but that's different, right?
Which use the bandwidth from routers, for instance. So there is always a gap between those two.
Yes, of course, because here we are not talking about virtual. You're talking about a virtual network that spans two different administrative domains. The outside network somewhere and the data center network. And these can be part of the same administrative domain or can belong to different administrative domains. If they belong to the same administrative domain, then when you allocate the virtual network end-to-end, you have to have resources both inside the data center and outside the data center. If they belong to two administrative domains and you want to have resources across all of these, then you have to create a virtual network in the data center and a virtual network outside of the data center and have them somehow interconnected.
Okay, thank you.
You're welcome.
There is a with respect reference to the same slide.
I'm sorry, go ahead.
What is, could you please clarify the difference between a software emulated link and a virtual link?
I'm sorry, your voice is completely disconnected from time to time. Can you repeat?
Is it better now, sir?
Go ahead.
Could you please clarify the difference between a software emulated link and a virtual link?
Between a virtual link and what?
A software emulated.
Which slide are you referring to?
The same one. NIC.
Oh, the difference between a virtual link and a software emulated link. Okay. Well, again, a virtual link is a concept. Okay. And it can be implemented in many different ways. And a software emulated link is, you can think of it as one way of implementing or realizing a virtual link. In this case, it's a software emulated link because there is no physical link on which you're going to say, I'm going to create a virtual link, right? So it's just, you are in a software between the virtual, so typically, traditionally in a network, you will have, you say, for example, you have a physical machine, then there is a physical link that connects this physical machine to a switch at some port, right? In this case, everything is in software. There is no link between the actual machine, the virtual link, the virtual NIC, and the actual switch, right? Because it's not a physical switch, it's a software switch, right? So it's a software emulated link, okay? So it's something that looks or has the properties of a link, but it's not a physical link. It's all, you know, a software concept, okay?
Okay. And the virtual link is, it's still on cloud, it's not a physical link either, right?
A virtual link can be a software emulated link, like in this case, but it can be also a partition of a physical link. Okay, like a virtual LAN, for example.
Okay. So another question, could you brief on
No hearing you.
slide 11?
Slide 11, okay.
Could you please brief on that again? I wanted to know.
I cannot
When the network service provider is down, will the child network not work?
Could you please repeat the question?
Nobody's hearing the question, really. I think your voices get completely disconnected.
Sorry about that. In slide 11,
I am on slide 11.
the parent network and the child network, in the case of recursion, if the parent network stops working or if the network is down, will it affect the child network? The network plane has service provider different from that of plane 1?
Okay, let me try to repeat your question and tell me, because again, I'm not hearing you very properly, but let me try to repeat your question. I may get it this time. So you're saying that in the case of recursion, does a failure in the parent network affects the child network?
Yes.
Yes. Yeah, this is one problem. I think this is one. Typically, the failure can happen in the physical layer, like in the infrastructure provider network, and so, for example, a node fails or a link fails. The link is broken, and obviously this affects all the virtual networks that are supported on top of that node, right? So, for example, if you have virtual links that traverse that physical link that failed, then all the virtual links become unavailable. Similarly, if a physical node fails, all the virtual nodes that are supported on that virtual, on that physical node also fail. Okay, if the node is no longer in service, then any virtual network supported by that node also disappear at the same time.
Although
now, in the case of recursion, okay, so you have one physical network on top of which you have one virtual network, and this virtual network is further partitioned to create child virtual networks. And this way you can have a hierarchy of virtual networks, okay, or multiple layers of virtual networks, okay? And then so, in this case, a failure in any of the underlying network, the physical network, or in the parent network will obviously propagate and affect all the supported virtual networks on top of that. So to your question, coming back to your question, if a failure happens in the parent network, then obviously, and the failure is related to virtual nodes or virtual links in the child network, then the child network will be affected, obviously.
All right, thank you.
Okay, I have a question here at Waterloo. Go ahead. Slide 10. Yeah. No. Yes. So I think so. The question from Waterloo here, I think, is the MVNP. The definition of MVNP here is very similar to the definition of SP in the previous slide.
So who does the instantiation of the it is like the next guy by this definition, Roger.
Yeah, so I think the question, follow-up to the question is referring to what I say in the video recording by providing an example of MNO like Rogers and an example of SP as FIDO, for example, that. And then the question then is, who really instantiates the virtual network? Is it Rogers or FIDO and whatnot? So, no, I think the definition here, I think you should think of a service provider more as the one that provides the end user services, okay? And in this sense, the MVNP not necessarily is the service provider. So it leases resources from the underlying infrastructure provider, but doesn't necessarily provide services, okay? So this is more a multi-layer virtualization type of thing, right? However, going back to the example, Rogers both provides end user, subscriber, but also leases resources to FIDO that provides services. So Rogers is both an infrastructure provider and service provider. So again, these roles doesn't mean that one entity, one business entity cannot have more than one role, right? So the question, who instantiates the virtual network? So again, the way it works, you have an infrastructure. Say, for example, you own antennas and routers and links and fiber and whatnot, right? And then the service provider, in this case FIDO, that's Rogers, has the infrastructure. And then FIDO comes and say, you know what, I'm gonna provide mobile network services. I want, for example, whatever. I want links here, and I want nodes there, and I want this particular topology with that many resources. This is called a virtual network request, okay? So it comes as a graph. You can think of it as a graph with nodes and links and capacity of the nodes and capacity of the links. This is given to Rogers, the owner of the infrastructure. And the Rogers will, by means of some algorithms and algorithms for instantiating or for mapping or embedding virtual network requests on its physical infrastructure, gonna come up with, with the virtual network that you need and provide access to Rogers, so Rogers can access, customize the resources and make them available to, and deploy services on these resources and make them available to the end users or the subscribers.
So the physical nodes are just virtual.
No. So here the question, follow-up question: the physical nodes are not leased. Is actually the virtual networks that are leased. No, the physical nodes can be leased. That will be, for example, hard partitioning. Say, I'm going to give you a full router, or I'm going to give you a full link, or I'm going to give you full antenna, or something like that, or the entire spectrum in one particular area. You can do that, or you can just, lease a subset of that. Say, for example, I have so much spectrum, and I'm give you that many of the spectrum, a subset of the spectrum, a particular frequency band that you can use to serve your users on that particular frequency band. Okay, so what you lease is, the virtual network of use, not the virtual. The virtual network is the result of leasing resources, right? So the virtual network is composed of resources that are leased from the underlying physical network. Okay.
Quick question about the next slide.
Follow-up question about the next slide. Go ahead.
You said that the attributes are provided or
Well, I hear by attributes here obviously is, the nature of the infrastructure, right? So, or the nature of the attributes are inherited. Basically, if your nodes, physical nodes, are in particular location, these are attributes, right? These are location constraints that are inherited, as well as, for example, is it wireless, is it optical? All these, attributes of the underlying network are obviously inherited to some extent by the upper layer, by the upper layer. Although, of course, there is also some abstraction where you can hide few things. You can create logical links that do not have physical counterparts. Okay. Let me take another question from somewhere else, and then
I have a question.
Okay. Go ahead.
About virtual switches and VNIC from slide 27.
Go ahead.
So the VNIC is just used for creating multiple MAC address when a physical NIC can be only limited to a few MAC address.
Can you talk in the mic, because I don't know, you're looking at something. You're looking away from the mic. I can see you. How about you put the mic in front of you?
Okay. Could you brief a little bit on what VNIC is doing?
What is what?
What VNIC function is it just creating multiple MAC address and IP address?
Huh? The virtual NIC.
Yeah.
Yeah. So imagine you have multiple containers, multiple virtual machines on one physical node, right? And this physical node has a physical network interface card, right? So anytime these, for example, virtual machines have to communicate, for example, to write data in a disk or read data from a disk or communicate with other virtual machines, they have to go through this physical NIC, right? So this physical NIC becomes a bottleneck, right? If you don't virtualize the physical NIC, then all the IOs, input outputs, will be basically conflicting with each other between the different virtual machines, right? So that's why virtualization is useful here to achieve this isolation. Basically replacing or basically creating virtual NIC, virtual network interface cards. So basically to allow some level of isolation between the different, in this example, containers, so they do not interfere with each other. So that's why the virtualization of physical NICs into virtual NICs is useful. Okay?
Yeah.
Yes, go ahead, Bruno.
Can you please go to slide number 11?
Go ahead.
Can you please explain revisitation in detail?
Explain what? What do you want me to explain? Revisitation?
It's so bad today.
I'm sorry. Revisitation.
Yeah.
Yeah, revisitation. All right. So the question to repeat for everyone is that to explain the concept of revisitation. So revisitation here is, it's basically the idea where you can have two virtual nodes that are located on the same physical node. Okay, so you see here, if you look at the picture, you see that the dashed lines show you where a virtual node is mapped on the physical infrastructure. And in this case, two nodes, virtual network 2, are both located on the same physical node. Okay? And that concept is called revisitation. Basically, you are revisiting the same physical node when you are establishing your virtual network topology. Is that clear?
Yeah, okay. And can you please go to slide number 67?
Slide number what?
67.
67.
Yeah.
Well, we have, I think the mic that you are using in Toronto is, there is a problem. It just cuts a lot. So 67, you said?
Yeah.
Go in there. There you go.
So in order to place virtual networks onto the physical network, you have mentioned in the video lecture that we need some location as well as the bandwidth constraints. So these constraints must be mentioned in the virtual infrastructure or in the physical infrastructure.
Oh, the location constraints.
Yeah.
I didn't say that we have to have location constraint, but typically you do have location constraint. Let's take again the example of FIDO that goes to Rogers and says, I want to establish a virtual network. FIDO has obviously, an idea where it wants the services to be available, where the customers are going to be, right? So because of where the customers or the end users are going to be, then it knows more or less where the actual virtual nodes should be located geographically, physically, okay? That makes the location constraint. And this location constraint is actually provided by the FIDO, which is the service provider, says, you know what, I want a virtual network, and this virtual network has the following topology, has, say, 10 nodes and 20 links connecting these nodes, and I want this node to be located physically, for example, within, say, for example, 10 kilometers of this area, right? That makes a location constraint. All right? And now, when the Rogers, the infrastructure provider, will try to map, will basically create the virtual network for FIDO, it's going to try to satisfy this location, or it has to satisfy this location constraint. It has to find nodes that satisfy the location constraints, but also satisfy the capacity constraints, how much bandwidth and whatnot, et cetera, and then provide the virtual network accordingly. So the location constraint is due to the service provider. It is provided as part of the virtual network request, and it is taken into account by the infrastructure provider when it does the virtual network embedding or the virtual network creation or instantiation or mapping, if you will. Okay?
Okay.
A question here in Waterloo? 36? Thirty-six.
How do they share the open cement? Like if both of them are cement, they may create how they Like if there are like two viruses from two different range of each other's range. And if both of them are making at same frequency band, they may like interfere with their signal.
Yes.
It may create a very high background sound.
Yeah. What does this has to do with virtualization?
Like how they share the frequency band. Yeah, it is more about problem.
First of all, of DMA, if you are referring to this slide, is not really so basically it's you're talking about like the
frequency band hour.
Yes. Yes. So they do not, by definition, if we're talking about two different providers, then they should not be interfering with each other because it's regulated, right? Who can use which? Yes, and then but within the same network, you can also have interference between different users that are using the same, that are basically supported in the same frequency band, and that's basically why you need partitioning techniques. And this is, for example, how it is done in this case, right? Where you basically you do the partitioning at the same time in the frequency and in the time domain, right? Where you allocate different slots to different users. This is OFDM, the traditional orthogonal frequency division multiplexing, where basically you allocate frequency. You allocate basically to different users a certain number of time slots, but they get the entire spectrum for them for that time period of time, right? But the OFDMA, which builds on that, but improves on that by allocating now different frequency tiles to different users at the same time, and that's basically improves resource utilization while in the same time avoiding interference, right? So in this case, the users do not interfere with each other, right? So they can use, and there are different techniques to avoid interference. Also, there are the guard channels in between that avoids the overlapping at the border of the frequency bands or sub bands and whatnot. So there is a lot of technology that avoids for different users to interfere with each other here based on this allocation. Okay, another question from Waterloo? Slide 54.
Service, the packets are encapsulated, so it works with normal IP. Why did
So the question from Waterloo, looking at slide 54 here, this is for provider provisioned virtual private networks. The question is if IP is used as a network here, and so what? Traffic is encapsulated into IP packets?
Yes, normal routers should be able to handle this, right?
So his question is, why do we need the PE, which is the provider equipment that is deployed to provide VPN services should be VPN aware, and so isn't that just using IP can take care of that simply? And the answer is obviously no, because here in this case you are basically providing different users to be routed on different virtual private networks in the core. So see, you have multiple tunnels or virtual circuits that interconnects these PEs, right? And so the PE is the endpoint of these virtual circuits, and then supports the end users. So why it has to be VPN aware? Because all these different users can be using the same address space, right? Okay, and then so you need to make sure that there is no ambiguity in terms of who basically to which VPN service a particular packet that is received belongs and where it should go, right? Because IP gonna just follow whatever, right? So for example, if you are using a private IP address scheme in your, say you have say an organization where you have multiple sites, this is typically happens, or this type of services are useful when you have, say, your organization have multiple sites. One is in Europe and one in whatever, Asia, and one in the US or different parts of Canada. And then you have your whatever resources and networking, and you want to communicate between these different sites in a private manner somehow, right? By providing some guarantees between these different sites, right? And you may be using, for example, private IP addressing in your network, right? And be able still to.
The adversary is inside the payload of the packet. Suppose this is a PGP, so the packets that are routed.
No, here we are talking about layer 3 VPNs, right? We are talking about layer 3. This cannot be PPTP. No, so it cannot be. So this is layer 3 VPN. So the IP addresses are used to do the routing, right? And so if you just rely on a native IP network, then there will be ambiguity. And that's where the PE has to be VPN aware and be able to say, okay, this particular IP belongs to that particular VPN. Okay?
So the routing is done with the internal IPs, not the.
Eventually, you're going to route it through an IP network, but be able to know which destination PE should this particular packet go, right? And that's why you need to know that. Okay. Okay. More questions?
Yeah, based on this page, I get a question. Why is the PE as well as the terminals are belong to the provider's property? So,
why the PEs belong to the provider?
Yes, for instance, for Fidos or Rogers, and the customer property.
Well, I think that's not necessarily okay. I think Rogers. Okay, so these are more traditional telecom providers that provide this type of services. But why? Because they want to provide VPN services, right? So, for example, you buy that from Rogers or whatever company that provides it, per Canada. You say, I want to interconnect my different sites. And so they say we provide, VPN services, and you buy VPN services from them. So they provide equipment to deliver this service, right? And I was explaining now how this PE, support basically implement this VPN service across a wide area network.
So here you mentioned the BGP and the VRF are using the two ways to disambiguate the overlapping addresses. Are those two routing protocols routing protocol and the virtual switch, the virtual forwarding table are implemented in the PE?
Yes. So basically, no. I think BGP, as I said, is one way is to extend BGP, and so you can solve this disambiguate, for example, the routing when there are such ambiguities. But as I mentioned, this is probably I mentioned in the recording that this is not really the best approach because it requires you to change the protocol, right? And this is really a very time-consuming and cumbersome process. And that's why I said VRF is a better approach to do that, because if you remember, VRF is implemented is discussed maybe in another slide. I don't remember which one. And VRF allows you basically to deploy different routing tables for different address spaces, okay, that are physically constrained by the interfaces that connect to these different routing table, and automatically deals with the issue or solves the issue. Basically, using VRFs, which means different routing tables for different virtual networks, okay, that will eliminate the possibility of ambiguities when it comes to routing on IP addresses. Okay?
I have questions.
Yes?
Why the multi-protocol level switching is faster than the GRE?
Why? What?
Why the MPLS is faster than the GRE?
What slide? What slide is that?
Just 48.
48?
Yes. So,
where did I say it is faster than GRE?
So far, I see here that it's a for high-speed IP forwarding. We use this MPLS.
Yes, I said it's for high-speed IP forwarding. I didn't say it is faster than GRE.
Okay, so what is the main
Why
difference?
it's fast? Is your question why it is fast, right? Why we can say it's high-speed IP forwarding? Remember, in IP, the way it works in IP, how does it work IP forwarding, right? So you have a switch, it receives an IP packet, okay? And this IP packet has an IP header, and in the IP header you have an IP address, destination IP address. So far, so good?
Yeah.
So what you're gonna do? You're gonna extract this destination IP address, and then you're gonna look up the routing table for this destination IP address. Yes or no?
Yes.
Okay.
So far, so good? Yeah. So you have a routing table, and this routing table is indexed with destination IP address. So you extract the IP address of the destination IP address in the packet, and you're gonna try to locate it in your routing table. And in your routing table, typically the way you look at it, you look just at the way it works in IP networks. It's the longest prefix match. Okay, so you're gonna find the entry in the table with the longest prefix match to the IP address, destination IP address that you want to route. Okay, and once you find this entry in the routing table gonna tell you the packet should be forwarded to outgoing port XYZ, or to an outgoing interface out of the router. Okay? This is how it works in a traditional IP network. Now, the way it works in MPLS, okay, so MPLS, you can think of it as layer 2, layer 3, or in between type of protocol that speeds up the forwarding or make the forwarding faster, because instead of forwarding packets based on IP addresses, it's gonna do the forwarding based on the so-called MPLS labels, okay? So basically, the label is a fixed size field, okay? So already it's not variable size field like longest prefix match, okay? And because it's a fixed size field, the decision how to forward the packet can be done much faster, because we're talking about a fixed size matching here, right? So these labels are basically decided in advance, and they're added to the packets. So when the packet is received, then we just look at the label instead of looking at the destination IP address. And the label tells us how to forward the packet further. And this process happens like you're creating a logical tunnel between MPLS-enabled switches, where the packets are only routed based on label as opposed to destination IP address. And that speeds up the forwarding process. And that's why I say it's a high-speed IP forwarding. It has nothing to do with GRE, which is the generic, which is the encapsulation or the tunneling approach for whatever, creating virtual networks. Okay?
Okay. And so is related to the next question, is that how the label switching routing, how do they find the path? For example, in slide 49, in the next slide. Yeah, from router 4, how do they find the path? They know that they have two paths and they will go in two paths to the A.
Oh, this is slide 49 has nothing to do with MPLS, by the way.
Yeah, I just look at the graph and not exactly.
Yes, so the slide 49 shows you how it works in traditional IP networks, not with MPLS. That's not label switching. Just this slide is here to contrast with label switching. So in this case, and that's how it works in traditional IP networks, we route based on the destination IP address. Say, for example, router 5 and router 6 have packets to send to destination A, right? In this example. So the packets from router 6 are blue packets, and the packets from router 5 are red packets. Both red and blue packets are destined to destination A, right?
Okay.
So router 6 in order to forward the packets to destination A, they're going to send them to router 4. Router 4 going to look up the routing table and going to say, okay, the routing table, again, based on the destination IP address, and they say, for destination A, then the next hop should be router 2. So router 4 will send the packet to router 2. And then router 2, same thing, look up the destination IP address, which is A, and the routing table going to say, oh, in order to send this packet to destination A, the next hop should be router, I don't know here, router 1. Okay, so close to A. So it sends the packet to router A, and router A says, oh, this packet is destined to A, and A is directly connected to me, so I'm going to deliver the packets to A. Okay?
Okay.
Now, in MPLS, or label switched routing, the main difference is that with the idea of routing based on the labels and not the destination IP address, we can change the routing philosophy. And this is illustrated in this slide here. So what do you see in this slide? You see that it's exactly the same example as we have seen in the previous slide, except here that we can define a label-based switching that says that routes based on the source IP address as opposed to the destination IP address. So basically, we're going to say that any packet I receive from R6 should be sent to destination A through the blue path that is shown here. And that for any packet going to A, but coming from the source IP address XYZ from router 5 should take the red path. And you see here that using this MPLS, we're able, for example, to do some load balancing using 2 different paths, not relying on the destination IP address that will mandate always the shortest path and hence the same path. But now, because we are routing based on other criteria, other factors than the destination IP address, we are able to implement more, different and more sophisticated traffic engineering mechanisms, okay, or approaches, right? So in this case, you see, again, we have R6 and R5, both sending traffic to destination A, and their traffic is taking 2 different paths. Because the label here, the packet now, we make a decision about where to send based on the label. And the label tells us, okay, or the table that includes the label says us, any packet I receive from R6 has to be forwarded to R4, R3. And it tells us that any packet I receive from R5 now must go to R2. And that's basically what allows this, difference in the routing achieved thanks to this labeled switched routing. Is that clear?
Yes, but in this case, the blue path is decided by the network operator, or how?
Yes, it is decided by the MPLS routing. The same way, say, for example, everything is decided by the network operator, right? Even IP routing is decided by the network operator. And how it is decided? It is decided based on which routing algorithms it implements, right? So if it implements routing algorithm X, it's going to do the routing in some way, or it can be also decided based on the weights that are allocated to the links in routing algorithm ABC, etc. Of course, this is decided by the operator. In the case of MPLS networks, the operator has to design these traffic engineering things and decide the label switched routing to achieve the traffic engineering goals.
Okay, thanks.
I have a question.
Go ahead.
It was mentioned in the video lecture that the virtual switch cannot provide the same features as the physical switch. What are some of these features?
The virtual switch cannot provide what?
The same features as the physical one, as the physical switch.
Why is that? Because I think that's mainly in terms of the resource guarantees, right? That's the main big difference.
Okay, and in terms of
speed, of course, like now, there are actually a lot of several implementations, because virtual switches are typically. Are you talking about virtual switches in the sense like Open vSwitch implemented in software and things like that?
Yes, exactly.
Yeah, so of course software switches. The main difference with hardware switches in general, and how this has nothing to do with virtualization, obviously, software switches can be implemented and not be virtualized whatsoever, right? In this case, the main difference is performance. Hardware switches, are able to forward packets or data frames at much higher speeds compared to if you do it in software. That's the main difference, performance. And then in the case of virtualization, so that's basically the whole discussion we had before about hard versus soft partitioning, right? If the more the partitioning is done in hardware, the more you have guaranteed resources allocated to virtual networks, and the more it is done upper layers and in software and whatnot, the less guarantees you have and the less isolation you have. Okay? Next question? Yes, go ahead, Toronto.
In slide 67.
67?
Yes. When we augment the nodes in the augment the nodes in our virtual net embedded problem, how is the linear programming in this case done? I didn't understand the that was on the slide with infinite activated.
Okay, I think the question is about Vineyard, and the question is, if I hear you correctly, again, Toronto, we have an issue with the audio at your side. But I think if I understand the question correctly, you're saying you don't understand the augmentation and the infinity value that is on these red links, and how the linear programming is used to solve this problem. Is that right? Yeah. So let me tell you, if you want to understand how this works, I think the best way is to read the paper, because there is a published paper that speaks about that. There is a lot of details, but let me explain to you in a nutshell how it works here, okay? But if you want to know the details, my advice is to read the research paper, all right? So what is this about exactly? So what we see here is one fundamental problem in network virtualization, which is what? Which is the so-called virtual network embedding. What is the virtual network embedding? May I ask whoever is not speaking now to mute the mic, please? Because because of the background, I'm speaking, higher and higher and raising my voice, and I start really now feeling the heat. So that's much better. Wow. All right. Okay. So this slide refers to this fundamental problem of virtual network embedding, right? And virtual network embedding, you can think of it as given a virtual network request, okay? So in this particular slide, you see we have the virtual network requests. The service provider wants to deploy a virtual network, right? And he wants, in this case, a network composed of 3 nodes, A, B, C, connected in this specific topology. And the link capacity is 10, 12, 10. And the node capacity, packet processing capacity is 10, 10, 10, right? This is the request. So virtual network embedding is the problem of mapping this virtual network request onto the physical network. And the physical network is shown in the bottom part of the picture. It's actually in black, right? All illustrated in black. So there are nodes A, B, C, D, E, F, G, H. And what you see, the numbers are the residual capacity, how much capacity left on the nodes and how much capacity left on the links. So obviously, the idea of virtual network embedding is to map virtual nodes, the red nodes, onto the physical nodes, the black nodes, and to map the virtual links, the red links between the virtual nodes, onto physical paths in the physical infrastructure, which means it could be a sequence of physical links, all right? Now, virtual network embedding tries to do that while optimizing many factors. For example, optimizing resource utilization or maximizing the number of requests that we can satisfy on the same physical substrate. So it's an optimization problem, okay? And this optimization problem comes with different things. It comes with objective functions as well as constraints, such as capacity constraints, location constraint, et cetera, okay? So it is an optimization problem, and when we want to solve it optimally, right? Now, the problem is we cannot solve it optimally, at least not in polynomial time, and hence we cannot solve this problem for big size networks, all right? Okay? And most of the solution that exists out there solve this problem into 2 steps. The first step is to say, let's first map the nodes, okay? Put the nodes somewhere in the network, okay? And this we can use a greedy approach, right? Say, okay, let's, just place the nodes, and then once we have placed the nodes, then the idea is to say, let's now find map the links, the virtual links on the physical paths that interconnect these nodes, okay? And here there are different techniques used out there. For example, it can be as simple as the shortest path, the Dijkstra shortest path algorithm. It could be the K shortest path algorithm. It could be a multi-commodity flow type of problem. It could be modeled in many different ways and solve it in many different ways. I'm talking about the virtual link mapping here phase. So 2 phases, node mapping and then link mapping. That's traditionally how this problem has been approached in the literature. Now, the problem with that is that it's not optimal. Why it's not optimal? Because basically, as soon as you place the nodes, you already restricted your solution space, right? And by restricting your solution space, the solution you find at the end, mapping the virtual links, is at best suboptimal, all right? Then immediately you should tell me that then the best way, why don't we just map the nodes and the links at the same time, all together in one shot? I would say, well, if we do it in 2 phases, it's already NP hard. Doing it all together at the same time is even harder. It's very complex. It's very difficult, okay? And that's why it is done into 2 phases, all right? Now, in this particular solution, this is Vineyard. It's one instance solution of this problem. It is the first actually solution out there in the literature that tried to, to do it not in one shot, not in 2 completely separate phases, but in some coordinated manner. So what is this idea of the coordination here? The idea is to say, okay, I'm not going to just use a completely blind, greedy approach to place the nodes. Instead of that, I'm going to place the nodes, not immediately, but creating these meta nodes. This is the graph augmentation, all right? And the location of these meta nodes is determined by the location constraint. For example, the location constraint says that node A here, virtual node A here, has to be close to node A and C, or whatever, some geographical area. And in that geographical area, there is node A and C, physical node A and C. So we're going to place a meta node A, augment the graph with a meta node A, and create these red dotted links, virtual links, to node A and to node C. And do the same for the node B and the node C, okay? And that gives us my augmented graph. So infinity here is, because this is not a real link, right? So we put, this infinity thing. And then this becomes a mixed integer program, and then what we do in order basically to, and then we model it as a multi-commodity flow problem, okay, where you can find, you have multiple flows with different bandwidth requirement, and you want to optimally allocate that. And then the problem here is we have 3 links from this meta node to 3 different possible mapping for the nodes, for each of these nodes, right? So the idea here, we didn't fix whether the node A is going to be on big A or on big C. So we leave it open, and we find the paths without deciding in advance whether A is going to be on A or on C, right? And so this is the main idea, right? So do it in somehow at the same time, in some coordinated manner. So we leave the option of mapping the node little a on either big A or a big C. And we do that after we do the commodity flow, solve the multi-commodity flow problem. Now, at the end, we use a binary constraint on these meta links in order to make sure that only one of them will be selected at the end, which will decide the mapping of the virtual node on which physical node. Okay? Now, this is a mixed integer problem, and hence it is linearized using some, rounding and randomized techniques, and these are described in the paper. This is more like optimization technique type of work. I recommend that you look at the paper if you are interested in these particular details. But did you get the spirit of the idea here? Okay. Other questions?
I have a question.
Go ahead.
In slide 21, would you please give more details on the difference between forwarding table and address space?
Where is that?
On data plane partitioning, you say forwarding table and address space. I cannot distinguish between these two.
Oh, they are not two different things. Actually, they are basically you partition the address space by basically deciding what for example flow rules in the forwarding table are cover that particular address space. They are not two different concepts here. Okay, that's how we. So basically, for example, because the forwarding table includes forwarding rules, and these forwarding rules operate on the address space. Okay.
Can we consider address space as the broadcast domain?
Well, it really you can define it you can define it in many different ways, right? So it really depends what it can. So for example, if you take it really depends how you define the flow, right? The flow is defined on multiple things, right? Different fields, right? It could be the ports, and in this case, port numbers. It could be MAC addresses. In this case, we're talking about the broadcast domain, as you mentioned, but it could be also based on source IP addresses, source destination IP addresses. It could be any combination of that. So the address space can cover many different things. And the partitioning, you would say that any flow that corresponds to that, signature that covers a specific address space, then is handled by specific rules in the forwarding table.
Thank you.
Okay. Question Waterloo here. 69.
It's unused.
Okay. Yes. No.
It's unused.
Question or not?
No, like, does it maintain a translation of physical IPs and respective?
Okay, I think the introduction to the question has to be answered before you get to the question. So his question is, does FlowVisor maintain a mapping and ensures the translation between physical addresses and virtual addresses? And the answer is no.
Does it broadcast this packet to all the controllers to see like?
No. No. So, and then the follow-up question is: a new packet arrives to the system. Does the FlowVisor? The FlowVisor, you can think of it as a controller that sits in between controllers and the physical infrastructure, right? Between controllers, and the controllers are assigned to different virtual networks. All right. So, and the question is: when a new packet arrives, does the FlowVisor broadcast that to all the controllers, or not, or to a specific controller? Of course, it will forward it to the specific controller, right? Because again, you partition the flow space, and the flow space defines the flows, right? And then when you receive, FlowVisor knows which controller is responsible for which flow space. So when it receives a new packet, it has a particular signature. So immediately it knows that which controller should be contacted for that particular packet. Okay? No, it maintains which flow signatures are part of the flow space to which controller and which controller is responsible for that. Okay? More questions?
I have a question.
Okay, go ahead.
Slide 56.
56. There you go.
I couldn't understand the difference between provider provisional VPN and this IPsec. Both are encrypting at the edge routers and making a private connection over the internet, right?
It's more about encryption and security here. It's not necessarily the case in the virtual private provisioned virtual private networks. So here, basically, here the tunnel is based on the encryption mechanism. So you encrypt the traffic at the source, and it is decrypted at the end. So it doesn't have to be a provisioned network. It can be a provisioned network, but you can see, for example, here we have in this particular picture, a user that uses IPsec on its machine directly and communicate, for example, with some servers that creates a VPN, IPsec tunnel. So you can think of it as encryption that happens at the IP layer. You take a packet and then you encrypt it, and then you send it. You encapsulate it in another packet, and you send it so nobody can see, what's in that particular packet. So here, basically, the virtualization is achieved by means of encryption to some extent.
So is the tunnel which is created, is it like a virtual links over the public network?
Not necessarily. No, like in the provisioned VPN service, it could be a virtual circuit using MPLS, where there is basically some traffic engineering and label switched routing over the core network. In this case, no. You can be sending that on a native IP network, okay? The tunnel is logical tunnel, again, and it's only created by means of encrypting at the source and decrypting the traffic at the end. So it's basically shares the same IP infrastructure with everybody, but it's isolated from the other by means of the private encryption scheme that is implemented on the traffic between the end systems.
So the routers in the middle just treat it as the same IP packet, but they can't just treat it because it's encrypted?
Because the encrypted packet is actually, there are two types of implementation of IPsec. You can only encrypt the payload, or you can encrypt the payload and the header. If you encrypt only the payload, then of course you don't have confidentiality, because you know who is communicating with who, because you see the source IP address and the destination IP address. So if you encrypt only the payload, you are guaranteed data integrity and authenticity of the content, because only those that have the proper keys can decrypt the traffic, right? But the sender and the receiver are visible, so you know who is communicating with who. So you don't have confidentiality. The other technique, which consists in basically encrypting the entire packet, including the payload as well as the header, guarantees, in addition to integrity and authenticity, it also guarantees confidentiality, right? And in this case, if you are doing the encryption of the entire packet, if you want to route the packet through the internet, you have to encapsulate this original packet into another IP packet, okay? That will help you route the traffic. So you add another IP header on top of the encrypted full packet, okay?
But still this IP header has the destination IP address, right? So how is it secure?
How is it secure?
Like after you encrypt it, you put it in an IP header which should have the
encapsulate because see, you have here you have a networking device with the IPsec, right? At the end of the tunnels are in yellow in this picture, and then you have a networking device with IPsec. The source IP address is the one of the end user. For example, here the one of the very top, right? At the bottom. At the bottom you have end users. So the source IP address is that of that end user, and the destination IP address is that of the end user at the other end, the destination, right? Now, when the packet arrives to this networking device that implements IPsec, okay, it's gonna encrypt the entire packet, including the header, the source and destination IP address, and encapsulate that in another packet. The source of the packet now is the networking device, and the destination is the networking device at the other end. When it reaches the networking device at the other end, then the packet is decapsulated, decrypted, and sent to the destination.
I have a last question regarding this. When you're talking about the MLPS implemented routers and all of these routers with RPSec, do they treat the other packets from the public network normally, or are they just specialized for this purpose?
Who's specialized? Which devices?
Like the networking routers which implement IPsec, or the routers which implement NLPS?
No, these are not really in the core of the network. These are devices at the end system. Let's say, for example, at the say you are at Laval, that will be like a device that is provided by the campus network in Laval. It's not in the core of the network. And now, so for MPLS is different. MPLS, you will have MPLS switches inside the core of the network, and all the traffic go through both MPLS switches and normal switches. But when they get to an MPLS switch, then basically the label is used to make the forwarding decisions.
If something without the label arrives at the MPLS switches? Do they treat it normally and forward it to the other router?
Well, it could go it cannot be processed as an MPLS, right? So it can so it's only processed if there is an MPLS label. I'm not sure I'm getting your question here. What arrived?
If you said the MPLS routers are in the core system, which direct the MPLS packets, right?
Yeah, but see, look at the slide 48 here. It gives you basically the how it works, right? You have an MPLS header, and if you don't have the MPLS header, then the packet is forwarded just using the IP header, right?
Okay. Thank you.
Other question? One question you want to do here?
I have questions.
We have there is an ongoing question in Waterloo. Can you give us a minute? 28, 29, okay.
So it looks like instructs the place to some sort of and then
Let me try to repeat your question here. So what you're saying is, looking at this picture here, what happens in the kernel data path versus into the user space, right? And isn't that like redundant with what's happening in the controller? Yes, yeah. Processes open flow rules and whatnot. No. So I think your question here is basically what's happening on each path. Let me explain again what happened, and then basically, so again, so here basically what happened here is, for example, there is a packet that arrives, a new packet never seen before, arrives to in the kernel, right? So that's what the packet arrives from the NIC to the kernel thing, right? So here the kernel doesn't know this packet, right? And have not seen this packet before. So then it goes up to the user space, because here it's implemented like the calculation or the decision, the forwarding rule is actually is basically calculated or basically maintained in the user space by the OVS switch team, right? So that basically makes a decision. So then the packet goes down to go back to the kernel, and then it is forwarded to the next hop, right? Now, this information about how to forward this particular packet is then maintained at the kernel level, and that's more for fast processing. So if, for example, the packet with the same signature comes again, then this is forwarded directly by the kernel data path. You can think of it as caching flow rules in the kernel for fast processing of packets that you have seen before. Yeah, that's the open flow, that's the control plane, data plane. Yeah, the traditional control plane, data plane operations, yes. So they basically, it's going to send a packet in request to the controller going to install the flow tables, and these flow tables are maintained by in the user space as opposed to the kernel space. Yes.
The previous slide, the lecture, you said that that's bad and dedicated network hardware, but it's like the Linux kernel is not capable. So how is it that if Linux doesn't do that, if the kernel doesn't do that, how is it?
Doesn't do what?
Is something in the line
These already answered.
So the question here, let me just try to repeat the question. And so the question refers to something that is not in the slide, but something that I said in the video recording. Is that right? And I'm saying that for Open vSwitch can allow to connect multiple things, machines. Yeah, Open switch. Yeah, so that Open vSwitch can span multiple machines and interconnect with hardware, things that the Linux kernel cannot do, or something like that. I don't really remember what I said in the video recording, but I can tell you that obviously you cannot just simply have a Linux kernel basically support, for example, communication between say virtual machines that are not on the that are on different physical servers, right? Because so basically that's where the switch allows you to do that, right? So to span, basically to support communication across multiple machines. How is this different from installing an Open vSwitch at each machine? Why would you do that? Well, you have an Open vSwitch eventually there, but this machine supports multiple virtual machines, right? On a physical server, not at each virtual machines. You have one Open vSwitch on the physical machine that interconnects with Open vSwitches everywhere else, but that Open vSwitch allows to support the communication between different virtual machines on the same physical server, but also with virtual machines that are on a different server. Yeah, connects, not. Yeah, you are not really deploying one virtual Open vSwitch on multiple physical machines. Yeah. So it's the other way around. Usually you have one physical machine and you can spawn multiple things, virtual things. No. I think so. The question is clear now. So I think what he understood from what I said in the video recording is that unlike a Linux kernel that allows also to support communication between virtual machines, an Open vSwitch can span more than one machine, and he understood that if the Open vSwitch or the virtual switch is deployed on a cluster of physical machines. No, I think the meaning or what I meant is that the virtual switch allows to connect virtual machines running on multiple physical machines or geographically distributed physical machines, as well as virtual machines located on the same server, by the way. Okay, any other question? We have about 10 minutes to go, and then we start the quiz, okay?
Yes, slide 44.
Okay.
What do you mean by layer 2 overlay over a layer 3 network?
Layer 2 over layer 3 network. So layer 2 over 3 network is an overlay. So it's an overlay where basically, and it's shown actually, the picture illustrates exactly what it means, is because you can see that you have a layer 2 frame that is encapsulated into a UDP packet that is encapsulated into an IP packet that is encapsulated into a MAC frame. So that's what it means. It's layer 2. Basically, the useful data that is transported here in an UDP packet or a layer 3 packet is actually the actual frame, a layer 2 frame. So you are encapsulating, so you are overlaying a layer 2 network on top of layer 3. And why are you doing that? You are doing that because here you are talking about a data center technology, local area network technology. So what you see in this picture on the top is, multiple pods. So each pod, you can think of it as a layer 2 domain because it's under one particular switch. Layer 2 domain means that you broadcast the packet, you send this packet in this layer 2 domain, and everybody, all the nodes in that layer 2 domain will receive that packet, right? But let's say if you want to send a packet from pod 0 to a machine that is in pod 3, you can't broadcast it, right? Because that's not a layer 2 domain. You have to go to layer 3. So basically, you have to do routing, right? So in order to do that, basically, if you want to basically create virtual LANs that span a large number of virtual LANs, by the way, which is common in data centers, that span multiple layer 2 domains, then VXLAN is used. And how it is used? Basically, you extend a layer 2 domain to some other layer 2 to machines that are in another layer 2 domain by encapsulating the frame and identifying it with the VXLAN identifier, and then send it into an IP packet through routers to that other layer 2 domain. When it reaches that other layer 2 domains, then you decapsulate, you recover the original frame, and then you transmit it, you broadcast it like it was, like you are at the end broadcasting within the same layer 2 domain. Is that clear?
Yeah, thank you.
And page 70.
Slide what?
Page 70, 70.
17. Oh, 70. There you go.
Here and there. Why you mentioned this? Each uses entire address space. As previous calls, and for the OpenFlow doesn't forwarding via the addresses. It's only forwarding via the flow tables. So I don't understand.
Oh, yeah. The flow table. Yes, but the flow table operates on the address space.
Flow table.
The flow space, the address space, similar thing,
Okay.
So basically, in Flowvisor, you partition the flow space, and you say, okay, any packet that is, for example, with this address or port number or things like that, that's the address space, will be handled by a particular controller, right?
Okay,
Do you
so
agree?
I don't understand why this open vertex can virtualize the address space, but the
No. Open Vertex does not partition the flow space or the address space. I'm talking about Flowvisor. Flowvisor, because is your question why here we operate on the entire address space, right?
Yes.
Yeah. So Flowvisor does not operate on the entire flow space, because the way Flowvisor works, okay, is you partition. You take the address space and divide it into pieces and say, this piece is under the control of virtual network controller X, and this piece is under the control of virtual network controller Y. That's how you do it. So you are partitioning the address space or the flow space, okay, and allocating these different partitions to different controllers. In OpenVirtex, it doesn't work like that. All the controllers that are supported by OpenVirtex, it's the same thing. You can think of it as the same thing. It's also a controller that sits in between the physical network and the virtual network controllers. Now, it allows the controllers, the different controllers of the different virtual networks, to operate on the entire address space. Which means, in this case, and that goes back to one of the early questions we had from Waterloo, the OpenVirtex here has to maintain a translation, a mapping between the physical addresses and those that are somehow processed by controller X or YZ. Okay? So it allows all the controllers to operate on all the address space, but it has to maintain, you know, policy checks that says, all right, for translation between who's in charge of what, who is basically entitled to work on which address. Is that clear?
So in the flow wizard, if one address being used by one controller and the other controller cannot use the same IP address.
Yes. No, they can't use the same IP address, but it's basically, but yes. So that's the job of the Open Vertex, is to make sure that these conflicts are avoided. Yes.
Okay, thank you.
Yes. So I have a question in the last slide, very fast.
Okay.
The goal of network virtualization is isolation. So why do we need the interaction?
The goal of what?
So far, I understand the goal of network virtualization is isolation.
Yes.
So why do we have the need to interaction between them? And then next question is, what is centralized, decentralized, and hybrid market?
So why do we need interactions between them?
Yes.
Yeah, you may need interaction for various reasons. For example, you can have interaction between virtual networks in order to spawn another service on top of them. Remember this recursive network virtualization? So you want maybe sometimes to create one virtual network on top on two different virtual networks to provide a service that spans a larger geographical area or some whatever other properties. And so how the sharing of information between virtual networks should take place. It may be interesting to understand how this can be done. And then the next question was what? Economics?
Yes, the last sentence. Centralized, decentralized, and hybrid.
Markets.
Yeah.
Oh, okay, so basically here you have sellers and buyers, right? You have the infrastructure providers that lease resources, and then you have service providers that buy these resources. One sell resources and one buys resources. So that's a market, right? And you have many, many infrastructure providers, and you have many, many service providers. You can model that as a market, right? It could be an auction, it could be different, whatever market mechanism. And you can implement that in a centralized manner, or a decentralized manner, or a hybrid manner through brokers or whatnot. So you need basically, if this to become a reality and deployed at large scale, you need mechanisms and infrastructure to support this type of markets, and algorithms that allow to optimize, you know, the sales and the buying of resources on this market. Is that clear?
Okay, thanks.
All right, one very last question from Waterloo, and then we close the session for the quiz. Go ahead. Well, not really. As you see here, if you look at the table, it compares FlowVisor and the Open Vertex. So one of the advantages of Open Vertex over FlowVisor is that it basically supports recovery from failures, because you are maintaining all this extra work and visibility into the network. So you can Open Vertex, for example, if there is a failure in the physical network, is able to remap, because it configures virtual networks, but it also dynamically can reconfigure virtual networks, for example, or finding alternate paths or creating backup paths. So this is inherent to how Open Vertex is implemented, which is not. You can do it on FlowVisor, but it's not part of FlowVisor. Yeah. You don't really, because basically you're restricted. If it's all partitioned, you have little dynamics, control of the dynamics. For example, changing configuration, changing topology. Why in this case you can, right? Because there is no, all the partitioning is maintained at the level of Open Vertex and translated to things when it has to go to the physical network. Okay, that's the main difference. And with that, I'm gonna close the interactive sessions. we have just enough time to run the quiz. So let me ask the operators and the profs in the different institutions to start the distributing the quiz for today's class.
Professor, how long for the quiz? 35 minutes as the last time?
Yes, like last time, 35 minutes.
Okay. So one more? No? That's very much here. Yeah.
Assignment سمت assignment برای تا دوشنبه تازه هست تازه امروز بخوام بشنم چی هست Have a good day. You too. I want to because how the algorithm, how the algorithm, yes, I'm just the vegetable question has the country and just which one. And how about this? This and that, then the what is the total? You can 40 plus. It's like 70. Okay, this is answer. Did you give it 0?
So we are finished here in Waterloo. So we're disconnecting. And have a good weekend, everyone.
You too, Shaba.
Okay, bye-bye.
Yeah. So we're gonna stop broadcasting.